What's going on, everybody? Mr. Diamond, and we are now picking up where we left off with kinetic energy, and we're going to talk about potential energy. Now, potential energy is our second type of energy, and I kind of mentioned this in class. It's a lot more complex than kinetic energy, not because the work necessarily is harder, but because abstractly it's a little bit more difficult to comprehend. For example, I know that this pen has kinetic energy when I'm wiggling it around, and it doesn't have kinetic energy when I hold it still. But for example, when I click this pen, if I hold it really close to the camera, and you can kind of see there's a spring in there. I hope you can see it. If not, I'm just kind of awkwardly blocking the frame. When that spring is compressed, it has energy stored in it, its potential energy. And that energy is different than the kinetic energy. And when I let go, it uncoils and it releases the energy. And when I lift something, if I drop it, it'll fall and it'll release energy. You can also make things like, where you take like popsicle sticks and you can make those like ninja star things. When you throw, they burst apart. We'll do that in class most likely. I just have to look up a video on how to do it. But that's also potential energy. The position they're in is what's giving them their energy, not like their motion. Think about one example of this would be like a boulder being suspended by a string. If the boulder was moving, we would say it has the potential to do work, or the energy was being exchanged while it moved. But we know that that suspended boulder also can do work. Not just when it's moving, but when it's suspended there, it can do work based on the fact that it could fall at any moment. And that falling would be the force of gravity displacing it. And as it's displaced, it's going to be moving over a distance with the force, and that's work. That means work would have happened on it. So the energy that is not from motion is therefore energy that could potentially be there. It's not energy that you can obviously see, but it's energy that at a future moment could be accessed or could be released in some way, shape, or form. And that's what potential energy is. Gravitational potential energy is probably the most common type. Gravity is the most common place that we get potential energy from. Work is a force done over a distance, and in the case of gravitational potential energy, we're basically just combining two equations. I can derive this like on the board, but it's not really worth it. Work is equal to force times displacement. Force of gravity is equal to mass times gravity, and then the displacement would just be the height that something is placed. So the potential energy from gravitational energy, at least, is equal to the mass times gravity times the height. We care about how heavy is it, what is the gravity of the location that it's at, is it on Earth, is it on Mars, is it wherever, and then how high is it off the ground, because the higher something falls, the more the energy is going to be released from it. And we'll do a calculation about this. We'll do this one together in a video related to this. It'll be attached in the same section. And connecting to that gravitational potential energy, though, if you know the gravitational potential energy of an object, you also know how much work or energy was needed to get that object into that position. If you think about like, I think I get a little ball of sticky tack here. If we pretend this was a boulder and we take it from the ground and we're going to suspend it up in the air as a trap in some sort of weird like tomb that we're guarding our treasures of, Indiana Jones style. That boulder doesn't just spontaneously go to that higher position. It needs to be put there. Energy needed to be put into that boulder to lift it up in the form of kinetic energy or some other form of energy. I guess it could have been explosions. It could have been like a heat, something like that, or rocket propulsion. But energy needed to happen and work needed to occur to lift that boulder. It had to have a force move it upwards over a displacement, so work had to happen. And so if you know the potential energy of that position, you also know how much work was needed to put it there. Because again, to move something or get it to move, you have to put a force on it. Elastic potential energy is the only other kind we're going to be talking about at this point. The other ones are kind of more complicated, or we may get to later in the case of electricity. Not likely, but we may get to later. Elastic potential energy is the only other kind that we're concerned with, and it's commonly used in referring to springs. The major difference with most objects that are elastic or stretched is that it's easier to stretch or compress things a little than to compress or stretch things a lot. So what I mean by this is if you have like a spring, if you compress it just a little bit, if you just barely squeeze it in, that's usually not that hard, but completely compressing a spring down to where all of its spirals are touching usually takes a lot more work. So because of this, we know the force stored is related to the distance that it's compressed, because the further it's compressed, the more force it takes and the more force it's going to release. But it's also based on how resistant that spring is to change. How hard is it to compress the spring? And that value we call the spring stiffness constant, which is K, and we represent that as a Newton over a meter. How many newtons are needed per meter that you are compressing that spring? And we assign that value K, giving us this equation right here, which is called Hooke's law, H-O-O-K-E-S law. And it is the force of a spring is equal to the compression constant, or the spring stiffness constant of that spring, times the displacement, or the value that it has been compressed. This works from either direction. If you expand a spring, if you pull it apart, it's the force that it's going to need to go back and to pull out, and it's going to go the opposite direction. When you squish in the spring, it's the force to squish it, and it's the force the spring will push back out when it unsquishes. And that distance x is from what we call kind of the assumed starting position, or the normal position of the spring. If you weren't applying any force, let's say the spring was this long, if you compressed it this much, you would go, okay, well, what's this distance here? The distance between where the spring normally is and how far you compressed it. And if you expanded it, you would do the same thing. Distance between how far the spring normally is and how far the spring has been now that you have pulled it. That's what that x is going to be equal to. Because work cares about force being done over a distance, though, and we just said that the spring gets harder to compress as you push in further and further, we have to average it together. So this is kind of a deriving of what the equation is going to look like for work for a spring. But basically, we do an average force, where we say, well, the average force is going to be your initial force and your final force cut in half. Well, initially, the force needed at the very, very beginning is going to be basically negligible. There's no force. It's at a normal position. You don't need any force to keep it in that position. And then to compress it down, you would go, okay, well, what's the force needed to keep it at this position? And the average of those 2 points will be the average force going along the given path, if you were to average at any specific moment. So to do that, we say, well, the force of the spring at its given point is equal to Kx, and the force of it at the beginning when it's not compressed at all is 0. And then to do our average, we just add those two things together and divide by 2. Well, the second thing is 0. So really, we're just saying, okay, well, what's the force of the spring at that position? Divide it by 2, and then we multiply that by x. And in this case, because the force of the spring is equal to Kx, we get 1/2 Kx squared, where is equal to the work of a spring. It's the work done by a spring or to compress a spring, either one of those. So 1/2 times the spring stiffness constant times x squared, or the distance squared. And if you think about it, as a newtons over meters, and x is a meter squared, that means you'll have Newton over meter, meter squared. One of your meters will cancel from the squared, which is with the meter on bottom. You'll be left with Newton meters, which is the unit of work. And I'll go over that in class as well a little bit. We're going to do example problems over elastic potential energy as well. We've got one over force compressing a spring and one over calculating what the spring constant is. And that will take us to the end of our chapter over kind of introducing kinetic and potential energy. We're then going to be working on problems where they're related to each other, and this is where the math is going to start to get tricky. But for now, that's what I've got for the video. If you have any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.